Okay, the dumb iPad stopped again, so I've got to fill in a few notes here, so we'll do this relatively quickly. This is 7.4. Number 2, we're talking about the partial fraction decomposition. So the first problem, I'm going to go ahead and factor my denominator because that is the first step to the problem. You want to get your denominator factored. And then what we are doing is figuring out what two little fractions got added together to make this big fraction. So there are two smaller fractions, one with a denominator of x minus 5 and one with a denominator of x plus 3, that when they get added together, they would give you this big fraction with that as the common denominator. So to get this ball rolling, we're going to get rid of all of the fractions. So I'm going to multiply by x minus 5 and x plus 3 all the way across. Now, some of you do this in your head, and I'm okay with that, as long as you keep everything straight. But we need to multiply every single term by the common denominator. And then what will happen is we'll lose the denominator. So we'll have 5x minus 1 equal to a times x plus 3 plus b times x minus 5. Now I'm going to distribute over here. So I have 5x minus 1 equal to ax plus 3a plus bx minus 5b. Now keep in mind, this is an equation. And because it's an equation, the x's on the left side, and there are 5 of them, have to equal the number of x's on the right side, which are a plus b. So whatever a and b are, they have to add up to 5 so that I end up with 5x. And similarly, the constant term on the left has to equal the constant term on the right. So 3a minus 5b has to add up to -1. This is an equation. The x's over here got to equal the x's over here. The numbers over here have to equal the numbers over here. So now I have a system of equations that I can solve however I want. I think I'll use elimination because I like elimination the best, but you could use substitution or you could use Cramer's rule, whichever you wanted. So I'm going to go ahead and just multiply this equation by 5. So I have 25 equals 5a plus 5b, and -1 equals 3a minus 5b. So 24 equals 8a, and it looks like a equals 3. So then I can go back and say, okay, if a equals 3, then b must equal 2. Okay, so what is the answer? That is not the answer. The answer is the two little fractions that add up to the problem. So the two little fractions are a, so 3 over x minus 5, plus b, 2 over x plus 3. If you added these two fractions together, they would give you 5x minus 1 over the common denominator. Okay, let's look at the next one because it's a little bit bigger problem. So remember that you got to factor your denominator first. So factoring the denominator will give me -x squared plus 2x plus 4 over x and x minus 2 squared. So if I pull out an x, I'm left with x squared minus 4x plus 4, which factors into x minus 2 times x minus 2. Now, when you have a squared factor in your denominator, that introduces a little complication. My partial fractions for this problem will be a over x, b over x minus 2, and c over x minus 2 squared. When you have a squared factor, you must include the single factor, x minus 2, in this case, and then the squared factor. They both have to be included. That is only when you have a squared factor that you have to worry about that. Okay, so like before, I'm going to multiply everything by x and x minus 2 squared. And then I'm going to cancel whatever will cancel. Well, here, everything cancels, so I'm just left with this. Here, that cancels, so I'm left with a times x squared minus 4x plus 4. Here, one of those cancels, so I'm left with bx times x minus 2. And here, those both cancel, so I'm just left with cx. I really think it's smart to write it all down so that you keep everything straight. But that, of course, is up to you. Now, I still have some distributing to do here. So negative x squared plus 2x plus 4 equals ax squared minus 4ax plus 4a plus bx squared minus 2bx plus cx. Now, just like before, this is in the equation. So however many x squareds I have on this side, negative 1, has to add up to all the x squareds over there. So there's an ax squared and there's a bx squared. So negative 1x squared adds up to ax squared plus bx squared in order for it to be an equation. Now, the plane x's, I got 2 of them over here, and that has to add up to all of the plane x's that I have on the other side. So, 2 must equal negative 4a minus 2b plus c. And finally, any plane numbers I have to have, over here it's 4, has to equal any plane numbers I have over here, and the only one I have is 4a. Now, I think you can see how it would be definitely possible to have this kind of problem generate a big system of equations like we were solving on our calculators the other day. This one actually works out a little easier. They won't always, but if they don't, you've got your calculator. This one works out nicely because you can see that a must equal 1. And if a equals 1, then b has to be negative 2. And then I can figure out c by working all this out. So a is 1, b is negative 2, so it looks like c has to be 2. But again, you've done all this work, got a lot going on. The answer to the question is the fractions. So a over x plus b over x minus 2 plus c over x minus 2 squared. That right there is the answer to the question. those are called the partial fractions. Those are the little fractions that when added together give me the big fraction. All right, now we're going to graph. And this is old news, this is review. We did this before, earlier in the school year. So I'll go through it kind of quickly. So here we go. First thing we do is factor everything they'll factor. So looking at problem 3A, looks like I can factor it as the difference of squares. And nothing cancels, which simply means this problem will have no holes. And that's okay. If nothing cancels, we have no holes, move on. The vertical asymptotes, remember, happen when the function is undefined. And you get to be undefined by having a 0 in the denominator. So the things that would give me a 0 down there are 3 and -3. There are my vertical asymptotes. The horizontal asymptote comes from comparing the highest power in the problem, right here. X squared over x squared is 1. So my horizontal asymptote is 1. My intercepts come by, x-intercepts have a y that's 0, y-intercepts have an x that's 0. So if I plug in 0, I can see that my y-intercept is at 4/9. And if I let x be either 2 or -2, I get 0 for y, so those are my x-intercepts. Remember, x-intercepts come from the numerator. Vertical asymptotes come by setting the denominator equal to 0. X-intercepts or zeros come from setting the numerator equal to 0. Now, everything is in that picture that needs to be there, except the curve itself. So at this point, you can just kind of freehand it in. I hope you can see kind of a parabola-ish shape in there. And then on the outsides, you're going to have your little hyperbola piece up here and up here. Remember, the only places that you can cross an axis are the dots that you have already put on there. So you couldn't possibly draw this down here because you can't cross the axis. It has to be all up there. If you ever wonder what a graph looks like, please, please, please plot points. You never ever have to stew about a problem, about a picture. You can always just plot more points. All right, I've already started the next problem because I gotta get this done. So I've gone ahead and factored. Remember, step 1 is factor everything that will factor. So I factored everything, and this time I have a hole. So this picture is going to have a hole in it because I have a cancellation. And the hole will be at whatever canceled out. So your x value of your hole is going to be -1. After canceling, what I have left is what I graph. So this is what I'm going to be graphing, okay? Not the original problem anymore because I canceled it. Now I'm graphing that thing I have in the box. Okay. I'm going to go ahead and finish my hole though. I'm going to get that on there before I forget. The x-coordinate of the hole comes from what canceled. The y-coordinate comes from plugging in. So when I plug in -1, I'm going to get 4 on the top and 2 times -3 on the bottom. So I get 4 over -6, which is -2/3. So my hole is at the point -1, comma, -2/3. Now, let's fill in everything we did over there, but from this picture now. So in the numerator, I can see that if x is -5, I'll get 0. So there's my x-intercept right there from the numerator. I can see that if x is 2, I'm going to be undefined. So that's my vertical asymptote. And I can see that if I compare my x's, I have x over 2x. So my horizontal asymptote is at 1/2. And if I put in 0 for x, I would have 5 over -4. So my y-intercept is 0, comma, -5/4. Based on that information, I hope you can see this right here over here. We've done enough of these over the course of the year that I hope you can see that shape right there. Now, what's happening on that side of the picture? Well, I think you know it looks like this. Because it can't be down here, because it can't cross the axis anywhere but where I have already labeled. All right, one more. Now this next one looks incredibly easy, and it is. But it's going to be full of fractions, so I put it in here so that you understood it's the same concept even when there's fractions. So y equals 7x minus 2 over 8x plus 1. Nothing factors, nothing cancels, not going to have any holes. That's absolutely fine. We just don't have any. If I put in a 0 for x, I get -2. That is my y-intercept. How do you find a y-intercept? You let x be 0. Period. Every time. Now, what about my x-intercept? Y-intercept is x equals 0. My x-intercept, my zeros, come from the numerator. If you set that equal to 0, you get 2/7. So your x-intercept is 2/7. Your vertical asymptote comes from the denominator, and it looks like x equals -1/8 is going to be my vertical asymptote. My horizontal asymptote comes from here, so y equals 7/8 is my horizontal asymptote. Now, I'm going to connect my dots over here. There's no holes, obviously, no factoring, no canceling. And then I bet you know where the other piece is. The only place it can be, right here. So again, that was a very, very easy problem, but it has a lot of fractions in it. Nothing to worry about, no big deal. Okay, that takes care of 7-4. Have a great day.